Welcome to NPTEL online course on fractals and multifractals. So, in the last class we have defined the Hausdorff dimension by the Hausdorff S dimensional measure. For any set in R power n, the S dimensional Hausdorff measure have the jump point where the measure jumping from the 0 to infinity. That jumping point, that means that critical point we defined as the Hausdorff dimensions. So, some properties of Hausdorff dimension we discussed in the last class. So, we ended with the Hausdorff dimension is less than 1 in any set f in R power n, then the set is totally disconnected. So, in this lecture let us calculate the Hausdorff dimension for some special set, and we will discuss the equivalent definition of Hausdorff dimension. So, let me recall the definition. First, for any set x in R power n, S is a non-negative real number. For any epsilon greater than 0, we defined S dimensional Hausdorff measure as like this one. If this collection take the infimum, if delta tends to 0, this quantity we call it the S dimensional Hausdorff measure. So, there is a jump point where the S dimensional Hausdorff measure jump from the infinity to 0. That point S, the critical point, we can call it as the Hausdorff dimension of the set K. That means the Hs of K where it jump from infinity to 0 with the critical point, this S we can call it the Hausdorff dimension of K. This Hs of K may be 0 or infinity. So, Hs of K is maybe this lies between this, then like that we can define the Hausdorff dimension, and we discussed that if the set has Hausdorff dimension is less than 1 in R power n, then we can call this K is a totally disconnected set. The K is totally disconnected. That means we discussed the topology of the set K by the Hausdorff dimension. Now, let us estimate the Hausdorff dimension for some sets. Now, take the unit square in R power 2, unit square in R power 2. That means, if unit square we can take 0, 1 cross 0, 1. This R or x1 lies between 0 and 1 and y1 lies between 0 and 1. 0 and 1, take the collection of element xy x1 y1 such that x1 lies between here and x is lies between here. Take all the collection, this is the unit square. Now, take epsilon as 1 by 4, epsilon as 1 by 4. Cover this unit square by the closed ball of radius, that means closed ball means closed box of size 1 by 2, 1 by 4, not a 2, 1 by 4. That means we can take this one as 1 by 4, like this one we can take here 1, we need to cover like a closed ball of radius 1 by 4. Now, keep this corner, 4 corner we can keep it and removing remaining. So, we are taking the scale as epsilon as 1 by 4 and take the ball of closed ball of center x with the epsilon, that means this box S, each size is 1 by 4. Then the 16 square we can remove the remaining all, keep the corner 4. Then after the first iteration one can get this type of figure. Now, again for each square here subsquare we can divide as the 16 part and remove the corner one. So, in that case the epsilon equal to epsilon 1 is 1 by 4, epsilon 2 is 1 by 16. Then here you can divide as 4 16 boxes. Only keep this corner, remove the middle, it will give this one. Likewise you can apply on this remaining 3 square, then one can get different square like this one. Then next step again you can divide this one as 16 part, then one can get this type of square. So, continue this process, then after the nth iteration we can get 1 by 4 power n epsilon radius, we will get this type of number of sets in an r power 2, then take all the intersection. So, it will give the Cantor dust in r power 2, Cantor dust in r power 2. Now, let us calculate the Hausdorff dimension of this Cantor dust in r power 2. We are start with the unit square 0, 1 cross 0, 1, that means 0, 1 power 2. At each stage divide every square into 16 smaller squares with a quarter of the side length, 1 by 4 side length, and retain the same pattern of 4 square in the 4 corners and remove the remaining one. First step, second step, up to nth step we will get like this one, it goes on. So, at each stage k the number of square is 4 power k, side length of the square is 1 by 4 power k, side length is 1 by 4 power k, each of its length is 1 by 4 power k. So, diameter of the square is root 2 times 4 power k. We can apply Pythagoras, then we can get this diagonal as root 2 times 4 power minus k. So, now let us find the h1 of f. h1 of f is less than or equal to, which we will establish. Cover the set f by the 4 power k squares at each state k. Each square has the diameter root 2 by 4 power k. Thus, one dimensional Hausdorff content is, that means Hausdorff measure is h delta of 1 of f less than or equal to number of squares times diameters of power 1. So, the number of square is 4 power k squares of the diameter this one, which is equal to root 2. Therefore, h1 of f is less than or equal to root 2. The one dimensional Hausdorff measure is less than or equal to root 2. So, as k tends to infinity and delta tends to 0, we get this one. Now, this is the upper bound, we will try to find the lower bound of h1 of f. Let define the projection from R2 to R by orthogonal projection onto the x axis. That means projection of x comma y will project the x axis y. What is the Lipschitz problem? If you take x and y in 2 element in R power 2, apply these 2 element in this projection, the projection of x minus projection of y. So, projection of x goes to x1 and projection of y goes to x2, therefore, it is less than or equal to square root of x1 minus x2 plus y1 minus y2, the Euclidean distance in R power 2, which is less than or equal to x minus y. Therefore, the projection is the one Lipschitz does not increase the distance, that means the c value is 1. Now, by the construction in every vertical column there is always one square kept at each stage in the 4 corner, the left side the 4 corners. Now, therefore, the projection of f on the x axis, projection of closed interval 0, 1. If you are projecting this one with the x axis, it is the closed interval 0, 1. Using the Lipschitz property and the measure the Lipschitz map of f, that means h1 of f of E less than or equal to h1 of E. That means if f is a Lipschitz mapping on f, find the Hausdorff dimension of that means the Hausdorff measure of f of E and E, then the Hausdorff measure of this one is less than or equal to Hausdorff measure of this one, h1 of f of E less than or equal to h1 of E. It is true for all this, obviously 1 it is for true. Now thus h1 of f of E is the projection of f less than or equal to h1 of f, but projection of this f is 0 comma 1 because it project to the 0 comma 1, and h1 of 0 comma 1 is nothing but the length of the interval which is equal to 1. Therefore this quantity is greater than the 1. This quantity is greater than 1. So combining this one and this result, one can get the h1 of f is lies between 1 and root 2. Therefore the Hausdorff dimension of the Cantor test is equal to 1. So we constructed the Cantor test, which is a subset of r power 2. Their Hausdorff dimension is 1, whereas the r power 2 Hausdorff dimension is 2. We can generalize this Cantor test idea. If instead of dividing into 16 squares, we divide each square into m power 2 squares of side length 1 by m, and keep one square in each column. Keep one square in each column, the 4 corner when m equal to 4. If you have the m squares, then you can each column you can keep one square anytime, anywhere. The same argument shows that this type of set has the Hausdorff dimension as 1. Hausdorff dimension as 1. Now we took the element in r power 2 and their Hausdorff dimension is 1. The Hausdorff dimension is 1. Now let us try to calculate the Hausdorff dimension of the Cantor set. There are two arguments here we are going to propose. If f be the middle third Cantor set, as we discussed how to construct the Cantor set, if s equal to ln 2 by ln 3, then the Hausdorff dimension of f equal to s, which we need to prove. For that means the Hausdorff s dimensional Hausdorff measure is lies between 1 by 2 to 1. Fine. The Cantor set f split into a left part f union closed interval 0 comma 1 by 3, and a right part f intersection closed interval 2 by 3 comma 1. I think this is intersection. Clearly both parts are geometrically similar to the f, but scaled by the ratio 1 by 3, and f can be written as fl union fr, left part union right part. With this union disjoint, thus for s, hs of f can be written as hs of fl plus hs of fr. So this one has 1 by 3 power s as the lambda value. The scaling is lambda, and this is the measure hs of f, and this is the scaling is lambda power s, that means the 1 by 3 power s, and for the right part also the Hausdorff dimension is equal. That we already discussed the scaling property of Hausdorff measures. Assuming that at the critical point s equal to this value dh of f, we know that the hs of f lies between 0 and infinity. We may divide hs of f to get, for here you can see hs of f, we are getting, you can take 1 by 3 s as common, then 2 times 1 by 3 power s into hs of f. So both side you can divide, then one can get 1 by 2 times 1 by 3 power s. If you are taking ln on both sides, then s times ln of 1 by 3. So which implies s equal to ln 1 by 2 over ln 1 by 3, which is equal to ln 2 by minus ln 3. This will cancel, one can get ln 2 by ln 3. So that is here. So by using the left side and right side, we get this equation. From here we can get the 1 equal to 2 times 1 by 3 power s, which implies the S value is ln 2 by ln 3. So, for this critical value, Hs of S lies between this value, therefore, the Hausdorff dimension of Cantor set is ln 2 by ln 3, it is approximately equal to 0.6309. 6309. Now, we will go with the delta, the covering argument. We can call the interval of length 3 power minus k for k equal to 0 to 1 that make up the set Ek in the construction of F basic intervals. The covering mu I of F consisting of the 2 power k interval of Ek in the E1, E2 is the each step for the Cantor set of length is 3 power minus k, gives that if we are taking this as our delta and the Hs of F less than or equal to sum of ui power s, which is equal, this one equals number of interval is 2 power k of its size 3 power minus k 1 by 3 because it is 1 by 3 power k. So, it is take minus s, which is equal to 1 if s equal to ln 2 by ln 3. So, letting k tends to infinity gives Hs of f less than or equal to 1 for this star. To prove that Hs of f greater than or equal to 1 by 2, we show that take the summation ui power s, which is greater than 1 by 2 equal to 3 power minus k for any covered mu I of f. Clearly, it is enough to assure that the ui are intervals, and by expanding them slightly and using the compactness of f, we need to only verify the 11th one if ui is a finite collection of closed subinterval of 0, 1, closed interval 0, 1. For each ui, let k be the integer such that it satisfying this inequality, which is each diameter of each ui is less than 1 by 3 power k and 1 by 3 power k plus 1. In between, you can choose the ui such that the diameter is lies between these two number we can choose. Then ui can intersect at most one basic interval of Ek. Since the separation of this basic interval is at least 1 by 3 power k, if j is greater than k, then by construction ui intersects at most 2 power j minus k basic interval of Ej. Again using the 11, this becomes 2 power j minus k times 1 by 3 k less than or equal to 2 power j k times diameter of mu I power s. If you choose j large enough so that 1 by 3 power j plus 1 less than or equal to the diameter of ui for all I, then since the mu I is intersects all the 2j basic interval of length 1 by 3 power j, counting the interval gives that 2j less than or equal to sum of 2 power j minus k into diameter of mu I power j, which reduced to equation 10. Which extra effect the calculation can be adapted to show that Hs of f equal to 1, Hs of not ms of s, it is the Hs of f equal to 1. Therefore, this quantity lies between this Hs of f less than or equal to 1 and greater than 1 by 2 for this s value. Now, one can observe from this method 1, we can generalize the case. If f is written as the finite copy of fi, the set f can be written as union of I equal to 1 to m fi. The set is f is written as finite decomposition of some parts where each fi is geometrically similar to f. This is important, each fi is geometrically similar to f. but the scaled by the factor Ci. That means if you are applying the contraction, one can get this type of result. If you are applying the contraction on F, it will reduce to copy of itself. That means both are geometrically similar, and you can take the finite union of that Fi, you can get F. Then provided the Fi do not overlap too much, that not overlapping set, then dh of S as the number of S satisfying, dh of F as the number S satisfying, that means the Hausdorff dimension is a number S satisfying this equation. That means Hausdorff dimension can be calculated by its scaling dh of F equal to 1. For example, for the Van Koch curve, it is made up of 4 copy of itself scaled by the factor 1 by 3. Van Koch curve, we can scaled by the factor 1 by 3, 4 copy of itself. So here Ci is 1 by 3 for all I equal to 1, 2, 3, 4, and there are 4 copies. We have 4 copies. Therefore, the Hausdorff dimension is 4 times 1 by 3 power dh of Van Koch curve, if you carrying as k, which is equal to 1. If you solve this one, then one can get dh of k equal to 1 by 3 1 by 4. If you are taking the ln here ln, then dh of k can be written as ln 1 by 4 by ln 1 by 3, which is equal to ln 4 by ln 3. Similarly, if you consider the Sierpinski triangle, so here the scaling factor is 1 by 2. There are 3 copies in each stage. Therefore, here 3 times 1 by 2 power dh of Sierpinski triangle S equal to 1. Here if you are calculating logarithmic, then dh of S one can get as ln of 1 by 3 over ln of 1 by 2, which is equal to ln 3 by ln 2. This is the dimension of Sierpinski triangle. So, by using this method, if F is decomposed into finite copy of itself, that means if F is written as the finite union of itself, where each Fi is geometrically similar. If you define this as the contraction mapping, then the Hausdorff dimension can be estimated by using this equation. Just you can compare this method with the calculating the box counting dimension of the attractor generated by the iterated function system. Both are similar. Now, we will discuss the equivalent definition of Hausdorff dimensions. So, initially while defining the Hausdorff dimension, we define the diameter of the set. The set U is arbitrary set. By taking the delta cover of mu I, then we cover the set F. Now, you can think that if instead of the random set, instead of the arbitrary set mu I, if you take some specific structure, then what is the effect in the Hausdorff dimension? Let us discuss. Now, for instance, we could use covering by spherical balls instead of arbitrary set Ui. If you are considering the special cases spherical balls, then the Hs of F can be written as Bs of F, infimum of then Bi power S, where this smallness of Bi again the diameter of the spherical balls, then Bi is a delta cover of F by balls. So, ball of radius diameter at most delta. We obtained the measure Bs of f equals limit this delta tends to 0, Bs of f delta will give the measure of f with respect to the spherical balls, and a dimension at which Bs of f jump from infinity to 0, clearly Hs of f is less than or equal to Bs of f, since any delta cover of by ball is a permissible cover in the definition of Hf of s. Also, if any ui is a delta cover of f, then so bi is also a delta cover of f, where for each I bi is chosen to be some ball containing ui and of radius ui of diameter of ui less than or equal to delta. So, this is will get Hs of f less than or equal to Bs of f. Thus, sum of bi diameter of bi of s power s less than or equal to this quantity 2 times ui of power s, then you can take 2 power s out, then you will get this one, then Bs of f less than or equal to this quantity. If delta tends to 0, it allows that Hs of f less than or equal to Bs of f, which is less than or equal to 2 power s times Hs of f. In particular, this implies that the value of s at which Hs and Bs jump from infinity to 0 are equal, because this Bs is bounded by Hs of f and 2 power s times Hs of f. So, where this s jump from the infinity to 0, for same s value the both will jump in the infinity to 0. It is easy to check that we can get the same value of the Hausdorff measure and dimension if in one we use delta cover of just open sets or just closed sets, in which instead of the spherical ball you can use the open set and closed set, we will get the same measure. Moreover, if B is compact, then by expanding the covering set slightly to open set and taking a finite subcover, we get the same value of Hs of f, if we merely considering delta cover by finite collection of sets. Now, instead of the spherical ball and open and closed balls, now net measure or another useful variant in the Hausdorff measure. For the sake of simplicity, let f be a subset of the interval 0, 1. Then we can extend this idea into the any n dimensional square in r power n. A binary interval is an interval of the form r by 2 power k in the time the interval r by 2 power k comma r plus 1 by 2 power k open interval. The binary interval, this form we can consider for k equal to 0 to 1 infinity and r is varying from 0, 1 to 2k minus 1. We define m s of f with respect to the delta infimum among all the diameter mu I power s time ui is a delta cover of f by the binary interval. So, ui is a delta cover of f by this binary interval, leading to the net measure ms of f. Ms of f is defined as whenever this delta tends to 0, this will be the ms of f. Since any interval u is subset of 0, 1 is contained in 2 consecutive binary interval, each of length at most 2 times diameter of u, in just the same way as for the measure Bs, that means the spherical balls, Hs of f less than or equal to ms of f, which is less than or equal to 2 power s plus 1 time Hs of f. Again, for the same value of s, this Hs and ms will jump from the infinity to 0. Therefore, the Hausdorff dimension of f with respect to the h with respect to the m both are the same. Now, instead of this binary interval, Now we define some test function that we discussed in the geometrical progress of Hausdorff dimension. So this will coincide with the geometrical interpretation which we discussed in the previous lecture. It is possible to obtain a more precise indication of the dimension of a set F in R power n, that is just a single number, by introducing a dimension function that we can discuss this in the previous lecture. We can discuss the test function which is increasing and continuous. We define h of f with respect to hs, infimum of h of ui, that means diameter of ui, where ui is a delta cover of f. There is no change in the covering. We introduce the test function and applying the dimension function on the diameter of the covers, and h power h of f, when this delta tends to 0, this will converge into the h power h of f. If ht equal to t power s, this is the usual definition of s dimensional Hausdorff measure. If you are taking h of t as t power s, that means h of mu I equal to mu I power s. This is our usual definition of s dimensional Hausdorff measure which we discussed now. It will coincide if you are taking h of t equal to t power s. If h and g are dimension functions such that h of t over g of t tends to 0 as t tends to 0, then by argument similar to 8, h of f equal to 0 whenever h g of f is less than infinity. This lead to the notation of a dh of f, because there is a point between number h and g, the Hausdorff dimension jump from the infinity to 0. That number we can call it as the dh of f. So here defining the Hausdorff dimension by meaning of this, by mean of the dimension function, is finer characterization of the dimension property of f. Now let us discuss the Hausdorff dimension of some strange sets in the R power 3. Now we can just compare all the definitions of the Hausdorff dimension. So initially we defined the Hausdorff dimension by the, if you want to find the Hausdorff dimension of f, you can take the delta cover of the set f where the mu I is arbitrary set which has at most diameter delta. Mu I ui is the arbitrary set which has a diameter at most delta. Then we cover the f, we obtained the hs, that means the s dimensional Hausdorff measure. Then the where it is jumping from the infinity to 0, then we call it as the Hausdorff dimension. In the second definition, the equivalent definition, in the second one, instead of the arbitrary set, we have taken the spherical balls. Instead of mu I, we have taken the spherical balls. Then we obtained the Bs. So instead of the arbitrary balls, arbitrary sets, we have taken the spherical balls. Then we only changing the covers, we obtained the Bs, then we showed that Hs and Bs has the same S value, it is jumping from the infinity 0. Therefore, the Hausdorff dimension calculating by the cover of arbitrary set and the spherical balls are equal. Then we are covered by the net. For that we take the some basic interval in closed interval 0, 1. Then we cover the any set in R by these intervals. Then we obtained the same measure. Now in the more general version, it will give the more geometrical information of the about the set. For that we define the dimension function, whereas in the last lecture we had call it as the test function. We can call it as the test function. The test function has some h of is d as some test function, gamma of d power delta power d, like that we defined while discussing in the geometrical perspective of the Hausdorff dimension. Here the test function we can call it as the dimension function. It is the function from r plus to r plus. Here again the ui we are taking as the arbitrary set, not a spherical ball, anything. It is an arbitrary set of delta cover. Only change in the summation, instead of taking simply the sum of the diameter of ui, in the diameter we applied this test function h of ui of modulus of ui. That means the diameter of ui. We know that ui is greater than or equal to 0. We are taking always the diameter is greater than 0 we are taking. We are using the delta cover. So here why it is, it's general case, if you are taking h of t equal to t power s, then it is coincide with our first definition. So the h's of t, by taking this h of t as different function, we can get some information, more information of the set f. Then we showed that for the same value of if you are finding the Hausdorff dimension by using this one and the Hausdorff dimension using the previous all this cover, all are equal. Now let us discuss some example by using this dimension functions method. Then we will compare all the four the method to find the Hausdorff dimensions by means of its covers. Now let me define what is the Brownian path in R power 3. A Brownian path B from closed interval 0, 1 to R power 3 is a continuous but nowhere differentiable function. That means highly irregular curve in the R power 3. Simple Brownian path in R power 3, very irregular at all scales. The pictorial representation is given here. The Hausdorff dimension of the Brownian path in R power 3 is Hausdorff dimension of Brownian path is 2. Intuitively, the path behave like a two-dimensional object in terms of scaling. We are taking the Brownian path, it behave like a two-dimensional object in terms of scaling. Now, why h2 of Brownian path of 0, 1 equal to 0? h2 is 0. That means where it is jumping from infinity to 0, that point we can call it as 0. That means if you are taking two-dimensional measure, why it is 0. Cover the time interval 0, 1 by pieces of length delta t equal to r power 2. By Brownian scaling, distance between Brownian scalar b of t plus delta t minus b of t is directionally proportional to r. That means the number of pieces is directionally proportional to r power minus 2. The diameter of each pieces is r. So for a delta cover with delta is approximately, that means approximate by r, then if you are finding the diameter power 2, the number of pieces, sum of this diameter power 2, the number of pieces times diameter power 2, this is r power minus 2 times r2, which is equal to 1. This is the broad line case for dimension 2. However, Brownian path have extra fluctuations at small scale. More precise estimate using the law of the iteration law, iterated logarithm, so that for any epsilon greater than 0, one can cover the path with set of diameter less than r such that the sum of this quantity is less than or approximately equal to log of log 1 by r power minus 1 minus epsilon, which tends to 0 as r tends to 0. Therefore, h's of Brownian path of 0, 1 is 0. The source for the logarithmic correction, Brownian motion satisfy the law of the iterated logarithm. That means limit supremum of r tends to 0, supremum of t minus s less than or equal to r power 2, the distance between b of t minus b of s over r times square root of log 1 by r equal to c, where c is 0 comma infinity almost sure. This means that a spatial scale r, the typical oscillation of the path is not r, but rather a typical diameter at scale r is approximately r times this quantity. Thus the path is thicker than what r alone predicts by a factor this one. If we try to use the usual weight t square, the measure is too small, gives 0. We need to compensate by this logarithmic factor. So choose the dimension function h of t as t square of ln 1 by t. That means t lies between 0 and e power minus c. Then more refined calculation gives h of this b of 0 comma 1 lies between 0 and infinity. If we used t square alone, measure is 0. If we used t square ln 1 by t power 1 plus epsilon for any epsilon greater than measure is infinity. The exact critical case is this value, t square ln of 1 by t. So although Brownian path have dimension 2, they are logarithmically thinner than the typical two-dimensional surface, very thinner than the two-dimensional surface. Their size at scale t behave like this function t square ln 1 by t rather than t square, because usually we need to take the test dimension function as t power 2 in r power 2, but we are taking t square ln 1 by 2. So this shows that there are, what is the intuition from here? See, needs idea to two-dimensional surface. If you need to cover the approximately r power minus 2 balls of radius r, sum of r square terms which is equal to 1, then h2 is finite positive, that it will give the area of the surface. In the Brownian path, in the idea of two-dimensional surface, this is the idea to find the Hausdorff dimension. The number of box needed to cover r power 1 by r power 2 balls of radius r. Take the sum of r square term equal to 1, then h2 is a finite positive in this surface. In the Brownian path using t square needs 1 by r power 2 sets diameter proportional to r, but due to the extra wing links, this modulus of mu I2 tends to 0. You can see due to this motion, this going to do too thin for t square, too thin for this t square function. If you are using t square ln of 1 by 2, each set is effectively larger by the factor square root of ln of 1 by r. So the total weighted sum stay of order 1, stay the order 1. Just write with t square ln of 1 by 2. So the gauge function, that means the dimension function h of t is t square with s less than 2. Behavior of h is infinity. If t square, it gives 0. Too large path thinner than s. Too small path is thinner than t square. If you are using this function as this one, t square ln of 1 by 2, then h of s lies between some finite number h of h. Correct dimension function capture the true size. If you are using this one, you will get a too larger, overestimate the size. So the Hausdorff dimension deduct the power law scaling, here it is 2. The Hausdorff measure with t square is 0 because the logarithmic fluctuations. The refined the dimension function t square ln of 1 by 2 reveals the true geometrical size of Brownian paths. So dimension function provide a much finer geometrical distinction than the single number. So while using this the dimension function h of t, one can get the fine geometric description of the object instead of using the constant values. So the Hausdorff dimension is 2 tells us that path behave like a 2-dimensional object, whereas we are defining in r power 3, so that we are using the corrected the dimension function and capture their geometrical behavior, though the Hausdorff dimension is 2. So the dimension function h of t allow us to deduct subtle scaling law beyond pure power law. So as of now, in the box counting dimension as well as in the Hausdorff dimension, we have used the power law for finding the dimension, whereas here while using the h of t, one can get the more geometrical meaning of the object f. Now one can think there are different covering, but we getting the same Hausdorff dimensions. We getting the same outer dimensions. Now for finding the dimension, one can observe that we are covering the set by number of boxes, and we are just counting the number of boxes is required to cover the object. Maybe in the box counting dimension, we have taken all the boxes of our same size, whereas in the Hausdorff dimension, for all the different methods, we take the balls of utmost size delta. Therefore in the same covering, the ball may be the arbitrary size, maybe utmost delta, but it is a arbitrary size. So the box counting dimension is quite simpler than calculating the Hausdorff dimensions methods. Now we'll compare the Hausdorff dimension based on all the different methods. Now Hausdorff measure for the general covering. So here h of s is defined by getting mu I is a delta cover of f. Then where modulus of mu I is denote the diameter of ui, which is less than or equal to delta, at most delta cover. Then if delta tends to 0, will define the hs of f. Then it satisfying the monotone property, countable subadditivity, outer measure property. That means if the Borel set, it will satisfy the equality also. And Borel regular in r power n, as s increases, then hs of s is a decreasing function. Then there is a fluctuation point where the hs of f fluctuate from the infinity to 0. That fluctuation point we can call it as the Hausdorff dimension of f. This is for the general covering. By covering by the ball, we can take s and lambda greater than 0, or that maybe s is greater than or equal to 0. Then Bs of f is defined like this one. Instead of the general arbitrary sets, we are using the spherical balls. Here the spherical ball has the diameter as 2 times radius of Bi. We find the radius, then multiply the radius with 2, we will get the diameter. So diameter is 2 times radius of Bi, which is less than or equal to delta. That means radius we are taking at most delta by 2. Then s dimensional ball measure Bs of f, when this delta tends to 0, we will the Bs of s. Then comparing with this with hs of s, the hs of f and 2s of hs of f gives the bounds for Bs of f. So for the same value of f, then yes, then both will give the jumping from infinity to 0. So the Bs and hs are equivalent up to a constant factor 2 power s. Same dimension dh of f. So only the constant is 2 power s is the only variance. Then dyadic measure or net measure by covering the binary interval. For example, in r power 2 in the closed interval 0, 1, one can take this interval closed to open, then cover the set by this binary interval, we obtain the ms. Then ms of f is taking the delta tends to 0, one can get ms. Here also the ms is bounded by hs of f and 2 power s plus 1 hs of f. So every interval u in 0, 1 is containing in 2 consecutive binary interval, each of length is less than or equal to 2 times the diameter of u. Hence this sum is less than or equal to this sum. So ms and hs are equivalent up to the constant factor 2 power s plus 1. Here the constant factor is 2 power s. Again dh of f is same for this dimension and here, therefore all these three it is equal. And now in the dimension function h, the h is defined from r power plus to r power plus, it is an increasing continuous function. Here we are taking the diameter of the spherical ball, here diameter of the arbitrary set power s. Whereas here with respect to this dimension function, we are defining the diameter. Diameter, this function is defined on the diameter of ui. So for various dimension function, one can get the different HHF. That Hausdorff measure is defined as, if delta tends to 0, this will give the Hausdorff measure. If h of t particularly taking a ts, so the all will be equal by choosing the different covering. This is the generalized version of this one, whereas covering you can take arbitrary set, it will coincide with here by taking the ts. The covering is taking us the spherical ball and take h of t equal to t power s, it will coincide here. If you are taking the covering by the binary interval and h of t equal to t power s, it will coincide with here. So for the comparison between the Hausdorff measure, that means s dimensional useful Hausdorff measure and here, so h and g are dimension function with h of t over g of t equals 0 whenever t tends to 0, then hg is less than infinity and hh is equal to 0. There is a intermediate point, that means x grows slower than g near 0, then h measure is smaller, vanishing sooner. So associated dimension h is, where is the alpha, minimum of alpha h of f equal to 0 and supremum of alpha it is 0. This refines the dimension structure of an f beyond a single number. Different h capture finer scaling behavior at small scale. So if you are taking the behavior of hs of f as s versus for some fixed f, so where this hs of f jump from infinity to this point, that where it jump from the infinity to 0, this we can call it as the Hausdorff dimension of the set f. Now, so overall summary for hs and bs, ms and hh. Type of covering sets, here arbitrary set, here spherical ball or ball of radius less than or equal to delta by 2, binary interval in 0, in the r, if you are taking the r power n dimensional space, we can take the net with the finite product of the interval 0 and 1, similar interval. So here also the hh, it is the arbitrary set. Instead of arbitrary set, balls and binary interval one can put, will get the this two bs and ms measure in the ht by substituting h as the t power s. So here this will be the maximum dependency and will give the more geometrical feature of this the set f. So the relation to hs to with all the one, here bs has the relation 2 power s, here 2 power s plus 1 scaling. So note that here and here and here and here all the uh, all the 4 methods, the Hausdorff dimension of f is same. Here the constant factor is 1, here the constant factor is less than or equal to 2 power s, here the constant factor is less than or equal to 2 power s plus 1. Here not a constant, it depends on the function h. So here this is the standard theory to calculate the Hausdorff dimension of the set F. This is the geometric covering, this is the computational covering by the interval, that is a detect finer scaling and the more geometrical structure of the object. So the measure HS, BS and MS are different way to measure S dimensional size but lead the same dimension HF. The generalized measure HH using the dimension function capture finer scaling behavior and provides more detailed dimension profile of the set. So now in the next class we will discuss some properties of the Hausdorff dimension and compute the Hausdorff dimension for the different set in the next lecture. Thank you. For more detailed theoretical version is given in the Falconer, given in 2, and more geometrical perspective is given in Jens Feeder, the fractal books. Thanks.